Let's look at this testing situation a little bit deeper. And what makes it interesting is that sometimes there's judgment here because a test very often takes the form of look for something. If it's above a certain amount, we'll call it positive. If it's below a certain amount, we'll call it negative. That's a generic way of phrasing what very often happens with these biological tests. Case in point, cotinine is a metabolite for nicotine. I think something like 40% of the nicotine metabolizes to cotinine. So measuring the cotinine level, so the theory goes, in a person's blood will help us determine whether that person is a smoker or not. So you can ask a person, do you smoke? And use that in your studies, or you can measure their cotinine level, for example. Now, here are some numbers. They measured the cotinine level in this study on 1,539 smokers, individuals that they classified as smokers. And 78 of them had very, very low cotinine level, something between 0, less than 14 nanograms per milliliter. 133 of them had 14 to 49. 142 of them had 50 to 99, etc. So this is the distribution of cotinine level in smokers. 412 of them had more than 300. How about, if we're going to use this to discriminate smokers from non-smokers, how about non-smokers? Well, they studied 3,445 non-smokers and found that a vast majority of them, 3,300 of them, had cotinine levels less than 14, so somewhere in the 0 to 13. But there were some stragglers. 72 of them had between 14 and 49, 23 between 50 and 99, etc. There were even 11 down here, way down here, at more than 300. It looks like one way of differentiating between smokers and non-smokers is to come up with a cutoff and say below this cutoff we'll call them non-smokers, above this cutoff we'll call them smokers. So if we draw the bar graph, we see it here. The red, the non-smokers, and we see the vast majority, 90-some%, are in this category here, but there still are some down here. There still are some down there. So, but it does look sensible to use a cutoff. So, for example, if we use this cutoff here, if we use that cutoff here and said anybody to the left is going to be called a non-smoker, anybody to the right is going to be called a smoker, then we see that these people here will be incorrectly classified and these people here will be incorrectly classified. So instead of using that as my cutoff, why not move the cutoff here? Then I will pick up these guys, but I will also add these guys to the incorrect classification. So it all depends very much where you draw the line on what it is you're trying to do. For example, you should be looking at what is the impact of a false positive or a false negative. For example, if you are guardian of the blood supply for a nation, donated blood, and you test it, if you test a unit of blood and you falsely classify it as negative when you should be classifying it as positive, then what is the impact of that? Well, it depends what it is you're testing for. So, for example, if you're testing for the HIV, each unit of this blood typically gets used, impacts 8 people or so. You might be infecting 8 different people as a result of that. Same thing if you're testing for hepatitis. B. Whatever it is you're testing for. If you falsely label it negative, the consequences are dire. Whereas in the other direction, if you falsely label it positive when it should be labeled negative, what are you going to do? You're going to lose 1 unit of blood. Okay? Thus, the consequences are nowhere nearly as bad in that direction as the other direction. So, in these examples, false negatives are highly consequential, whereas false positives might not be. The other direction also works for antenatal tests, for example. You don't want to call false positives. But anyway, let's go back to the numbers and see how to quantify this uncertainty in labeling false positives, false negatives. And let's take a look at this one. Suppose we draw the line here. So suppose we draw the line at 13, 14, and call everybody below 14 a non-smoker and above 14 a smoker. Then what would we have? Well, the sensitivity of this procedure is, and let's say positive means you're a smoker. So the sensitivity is, of those 1,539 smokers, we will lose 78 of them. So 1,539 minus 78 is 1,461. So we will be correct in 1,461 over 1,539 of the cases. What if we moved the line down and used 50 as our cutoff? Less than 50, you'll be called a non-smoker, and more than 50, you'll be called a smoker. Then we will lose these 133 smokers. So the sensitivity now would be 1,539 minus 133 minus 78, and that gives us 1,328, divided by 1,539. And so on. If we lower the cutoff to here, then this is what our sensitivity would be. We lower the cutoff one more, this is what our sensitivity would be, and so on. So there's what happens to the sensitivity as we move the cutoff line down. Putting this into probabilities or proportions, we go from a 0.95 sensitivity to 0.86 to 0.77 to 0.64 and so on. So as we move the line down, our sensitivity goes down. But what you gain in the roundabouts, you should be losing on the swings, or vice versa. Then let's look at what happens to the non-smokers. So let's look at what happens to the specificity. Now, I'm going to set you up for the next graph, and there we plot 1 minus the specificity. So I'm going to look at 1 minus the specificity as opposed to sensitivity. No big whoop. So, all right, if we do the cutoff there, what about what happens to the non-smokers? 1 minus the specificity is how many do we get wrong. And this is how many we get wrong. We get 72 plus 23 plus 15 plus 7 plus 8, 9 plus 11. And the answer of that is 145. So we get these 145 wrong. So of the 3,445, we would get 145 wrong. If we move the cutoff down 1, then we get fewer wrong. We only get 73 of them wrong. Because now we picked up the 72, and the sum of these is 73. And moving the cutoff down like this, there it is. Expressing this in as proportions, then, or probabilities, then there they are. So 1 minus the specificity is 0.04. So in going down, in moving our cutoff down like this, we lose sensitivity, but at the same time, we gain specificity, because 1 minus the specificity is also going down. We can plot this, and there is the plot, and that is called the ROC, the receiver operator characteristic curve. This comes from World War II signal detection, but we just call it ROC now because nobody remembers what it really stands for. But anyway, there is the ROC curve. I've stopped it at 0.05. We could move it all the way up to 1. The ideal curve would be 0 here, shoot up to 1, and stay at 1. So that would be the ideal curve. In this case, it's not ideal. It's pretty good, actually, but it's not ideal. We lose this much. This is very often, this curve is used to evaluate. If you have two testing procedures and you want to evaluate the one versus the other, what people often look at is a quantity called the area under the curve. And that extends all the way to 1. And that's called AUC. That's the area under the curve. And presumably a test with higher AUC than another is to be preferred. Okay? But there it is. So that's an ROC curve. And you can use that to evaluate an imperfect test if you've got the choice on where you want to move the cutoff.